Here we see the same setup as before, except that the tube is now not flat, but it's rising, and it's open at the high end. This tube, of course the tube goes around and up to the container just as before. But what we have here now is a system that can measure the pressure with a good bit of precision, as we will see. Okay, you see right now the column is at 4 centimeters along the meter stick. If I simply put my hands on the bottle, that's going to increase the temperature in the bottle and thereby cause the pressure to increase. When I put my hands in the bottle, I exchange thermal energy with the walls of the bottle, which in turn conduct that energy through the vibratory motion of the molecules in the wall to the inside of the wall, where the vibratory motion interacts with the moving molecules and speeds them up. Okay, the particles in the walls vibrate faster, so that when the molecules in the container collide with those molecules in the walls of the container, they pick up energy and move faster. That's what we mean by an increase in temperature in the gas. Since the molecules are moving faster, they hit things harder, meaning they exert more pressure on the water here, which is then transmitted to the tube and so forth. And we won't go through all the details of that. I should say that the molecules speed up and they hit harder and also more frequently. It's important to understand that both of those things affect the pressure. In any case, to see how we can measure that with good accuracy, I just put my hands on the walls of the container. Now I'm not squeezing, and you'll be able to tell that when I release the walls of the container. You can see how quickly the container gains thermal energy and transfers it to the air. Now if I release, the temperature of the air will continue to go up for a short time while the heat, the thermal energy that I transferred, passes through the walls of the container. And then the walls of the container cool, and the container will come back to room temperature. And as it does, we can see the pressure again decreasing. And the pressure will go back right to where it started. I don't know if we'll watch it long enough to actually see it return to the 4 centimeter mark, but we'll watch it long enough to convince ourselves that it will return to the 4 centimeter mark. Now the reason the increased pressure increases the level of the fluid, well, again, we can simply talk about Bernoulli's equation. The altitude of the fluid is increasing. Now, it's not increasing, for a centimeter of motion here, it's not increasing as much as it would if the ruler was vertical, but it's increasing according to the slope here. So, if we move 1 centimeter along here, altitude changes by some proportion of that centimeter, and that proportion is the slope. And we'll see that in the write-up. The less the slope, the more sensitive this instrument is going to be. If I decrease the slope considerably, now you can see we're back to 6 centimeters. It should be fairly clear that we're on the way to 4. If I decrease the slope radically, then let's see how the sensitivity changes. If I put my hands on the system now, we see that the water rises much faster and further. We'll just move the apparatus over. Now when we did that, we kind of changed the elevation, and there was kind of a jump, since we're not really measuring this motion at the time. That won't really hurt anything. We see that the motion is much quicker. Now that's not because changing the elevation or changing the slope of the meter stick caused the gas to cool off faster. That's simply a result of the fact that we don't gain as much elevation per centimeter. And the elevation we gain is going to allow us to measure the pressure difference by rho GH. Okay?